This video is on logarithmic functions. So if you look at the top of your notes, it says consider the exponential function y equals a to the x. It's exponential because x is my exponent here. The question becomes, what is the inverse function of that? Well, to find the inverse, we would switch the x's and y's and get x equals a to the y, but there's no way to do the next step, which is to then solve for y. It's impossible to do that. So there's no algebraic operation that we know of to solve for our y in that first step of our finding the inverse to that exponential function. So instead, we define a new function as y equals log base a of x. And this is the definition of a logarithmic function. So in other words, the logarithmic function is the inverse of the exponential function, but since we can't solve for it, we define it in this way. So you need to remember and memorize something right here because it will help you later when you are converting from exponential to logarithmic. And that is, some base raised to an exponent is equal to n is the same thing as saying that the exponent is equal to the log in some base of n. And let me show you what I mean. Here's an example. If 2 to the third equals 8, which it does, 2 to the third power is 8, then another way to say that would be the log of 8 in base 2 is equal to 3. So let's look at the placement here. Here is our base. That's a pretty easy placement. The exponent is sort of like the answer here. It's like this is all about the exponent. And then what was the answer here is what we are taking the log of. Going the other direction, if the log base 3 of 9 is 2, then what you can say is the base, which is 3, to the exponent, which is 2, is equal to 9. So let's practice going back and forth a little bit. If we had 4 squared equals 16, the way to say that with logs would be the log of, what is the base? 4. The log base 4 of 16 is the exponent 2. Those two things mean the same thing. Here we have e to the b equals 9. What we would say is the log, what's our base? Of base e of 9 is equal to b. Again, the exponent becomes like the answer. Now let's go the other direction. If we had log base 3 of 81 is 4, the way to say that, and I think it's actually easier to go this direction, start with the base, raise it to the exponent, and then you get the answer. The answer is what we took the log of before. So here, start with the base, raise it to the exponent, and you get the answer, which is what we took the log of before. So in this next section, it says find the exact value of log base 2 of 8. And here's what we're going to do. We're going to say that it's equal to y. We're going to call that y. And then we're going to rewrite this exponentially, which would be to say 2, that's the base, to the y equals 8. Well, I can change this 8 into the same base as 2. And if I can get my two bases the same, then I know my exponents are equivalent. So 2 to the y is equal to, how can I break down 8 into a base of 2? It's 2 to the third. So what does that tell me? It tells me that y is equal to 3 because my bases were the same. Therefore, the exponents, let me show that in a different color, y and 3 have to be the same. Here we have log base 25 of 5 equals y. Changing it again into exponential form, we would have the base 25 raised to the y is equal to 5. Now, this one is a little tricky. I can't turn the 5 into a 25, but I can change the 25 into a 5. So that is 5 squared to the y is equal to 5, and we could say to the first power. Now I have the bases the same, 5 and 5, and how do you do inside-outside exponents? We say 5 to the 2y is equal to 5 to the 1. The bases are the same, therefore 2y is equal to 1. I divide by 2, and we get y is equal to 1/2. These are a little tricky at first, but remember your goal. I'm going to write this down. The goal is to make the bases the same, because once those bases are the same, you can set the exponents equal to each other. So let's look at this one. Log base 1/16 of 2 equals y. So we're going to say our base 1/16 raised to the exponent to the y power is equal to 2 to the first. Now this one is tricky because we have to think, do you change 2 to a 16? No, we can't break down a 2 into a 16. We have to take the bigger one and break it into the 2. So 16, if I go up here, 2 to the fourth is 16. So 2 to the negative fourth is equal to 1/16. You have to know those negative exponents. So what I'm going to say is, I'm going to show 1/16 as 2 to the negative fourth to the y is equal to 2 to the first, or 2 to the negative 4y is equal to 2 to the first. Now my bases are the same, so what I say is the exponents are the same. Negative 4y equals 1. I divide by negative 4, and I get y equals negative 1/4, and I ran out of space. There's not really space there to do those. So let's look at some more of these. They get a little bit trickier. Here, I want to write this exponentially, so I'm going to set it equal to y, and I'm going to say my base to the y is equal to 2 to the first. Well, that one's easy because my bases are already the same, so I know that just y is equal to 1. So that's kind of a unique one. The log base 2 of 2 is 1. So when you take the log of something in the same base, you get a 1. Let's look at this one. Set it equal to y. Our base to the y is equal to 1. Well, what can I do to make these bases the same? Well, I can show 1 as 2 to the 0, can't I? I want my bases to be the same. So now my bases are the same. I know that y is 0. Here, I have my base of 2. Let's set it equal to y. Raised to y equals negative 4. Is 2 to any power equal to negative 4? Think about it. 2 to the 0 would be 1. 2 to the negative 1 would be 1/2. 2 squared would be 4. I can't get a negative. This one can't be done. It's impossible. Not dome, but done. Can't be done. Finally, let's look at this one. Is 2 to some power, we call y, equal to 0? Is there anything I can raise 2 to get 0? No. That one also can't be done. All right, so let's look at our next page. And we see some talking about inverse functions. And as it says, as with all inverse functions, the domain of the logarithmic function is equal to the range of the exponential and vice versa. And by the way, that would be 0 to infinity. And the range of the log is equal to the domain of the exponential, which is negative infinity to infinity. So it says here, find the domain of each logarithmic function. So let's use that knowledge to find the domain of this log. I know that what I'm taking the log of, x plus 3, its domain is the same thing as the range of the exponential, which is 0 to infinity. So x plus 3 must be greater than 0. I can solve that by subtracting a 3, and I know that x must be greater than negative 3. And the reason is right here again, because the range of the exponential is 0 to infinity, and that's the same thing as the domain of the log. Here, I know that negative x must be greater than 0, but I want to know what x is, so I divide by negative 1. Dividing by a negative causes my sign to flip, and here I know that the domain is x must be less than 0. All right, let's look at the graph of the logarithmic function, and there are some instructions here for you using your graphing calculator. So if you need to pause for a minute and get your graphing calculator, make sure that you have it available. I just got mine. It says graph y equals log base 2 of x, y equals 2 to the x, and then graph the function y equals x in your graphing calculator. And then sketch those 3 graphs on the first coordinate plane that is shown here. So we're going to do that right here. So I want to show you how to put this in your graphing calculator, and depending on your operating system, you actually may not have this choice. So if you don't, you watch what I'm doing and you can still sketch it and get the same results. I'm going to move my graphing calculator over, turn it on. We first want to enter y equals log base 2 of x. Now your graphing calculator comes programmed with log base 10 and log base e automatically. So to change that base to base 2, I'll show you how you do that. So we're going to go into y equals, and we want to then go to our math button, which is right here. You hit math, and if you scroll down, you will see, you will get down to after 0, 9, 10, and then there's a log base. Pick that, and it allows you, it sets up your calculator to choose the log. And I want base 2, and then I want to take log base 2 of x. So there's my first function that I am inputting. The second one is y equals 2 raised to the x, so 2 raised to the x. And then the third one is the function y equals x. Now I've already set my window, so let me show you how you should set yours. If you go into window, I want you to set x min at -3, 3, x scale 1, and then -4, 4, 4, y, and then y scale 1. When you hit your graph, remember it's going to go in the order of the log first, and then its inverse, which is the exponential, and then the line y equals x. So let's take a look. Here is our logarithmic function that you can see graphing. Here is our exponential that we've talked about before in prior videos, and there is the line y equals x. So let's sketch that on here and look at the points that our graph goes through. So first off, it goes through this point. Now remember, we're doing it as base 2. So it looks like this. We have the point 1, 0. We have the point 2, 1. And then we have the point, and mine it didn't sketch quite exactly right, but we have the point 1/2, -1, and it continues down here, never touching the axis. That y-axis is an asymptote, a vertical asymptote, and this is a -1, by the way. This is our function y equals log base 2 of x. Now, in a different color, let's do the exponential. It goes through, we learned this point, it looks something like this. It goes through the point 0, 1, notice just the opposite of 1, 0. It goes through the point opposite of this, -1, 1/2. And it goes through the point, instead of 2, 1, it goes through the point 1, 2. So you can see that they are inverses because we learned that inverses have their x and y's just reversed. Now I'm also going to sketch this line right here. This is the line y equals x, and you can see that my logarithmic function in purple is a reflection of my exponential function in green across that line y equals x. Now we're going to do the same thing. It's a little harder to see. With our base, instead of being 2, it's going to be 1/2. So let's go back to the graphing calculator. Let's go into y equals. We're going to just go ahead and hit clear because I want you to see how to do this again. And we are, in fact, let's clear the first 2. We'll leave our y equals x line in there. So we go back up here. Now remember where I retrieved the extra log bases. I went to math, and then I scrolled down to a, whoops, went past it, which is right there, log base. Now I'm going to do 1/2 as 0.5 just because it's going to be easier to type in. Okay, and we're taking it at x. And now I want to type in y equals 1/2 to the x. So again, I'm going to do 0.5 raised to the x. And we can leave our window the same. So go ahead and hit graph. There is our log. Here is our exponential. And here is the line y equals x. So let's sketch that in. Our function y equals log base 1/2 of x also goes through this point, but unlike this purple where it was going this direction, it goes through like this. Let me see if I can get these right. These points, I'm going to try. Remember, mine's just a sketch. That is y equals log base 1/2 of x. And then in green, we have the exponential that we know is always going to go through that point 0, 1. It goes through the point 1, 2 instead of the opposite 2, 1. Or excuse me, it goes through the point -1, 2 instead of 2, -1. And then it goes through this point right here, 1, 1/2, and it looks something like this. Now, it's harder to see that these are reflections, but they are. And when I put in the line y equals x, if I had drawn my graphs correctly, they all would have crossed right there. You will see that they are also reflections of each other across that line, but it's not as easy to see as it is right here. So it says conclusions. We know that log base a of x and a raised to the x are inverse functions. That's one thing we know. And we also know they are symmetric to y equals x, or across the line y equals x. So those are the two things that we showed in that graphing calculator. Now on the next page, we're going to look at a special case of the log function, just like we had a special case of the exponential. We have special case logs too. And the first case is called the natural log, and that is when our base is e, and we talked about that in the section on exponentials. So when we have base e, we use ln. Instead of writing log base e, we write ln, the natural log. And it's so, oops, let me bring that down. It's so common, and it's very uncommon to write log base e. So the definition is, if the base of a logarithmic function is the number e, then we have the natural logarithmic function. This function occurs so frequently in applications that it's given a special symbol, ln, like I showed you. Y equals ln of x if and only if x is equal to e raised to the y. So remember, when you see ln, it means log base e. So in our graphing calculator, again, let's get it. You are asked to graph y equals ln of x, y equals e to the x, and y equals x. So let's take a look. Let's do that. Go into y equals. Go ahead and clear everything but the last y equals x we're going to keep. Let's go up, and the first thing we're going to enter is y equals ln. You actually have a button. It's so common. See this ln button right here at the bottom here of this screen. So we're going to say y equals ln of x. You don't have to close the parentheses, by the way. I'm going to, but if you don't, it assumes that you intended to. Next, we're going to type in y equals e to the x, and e to the x is the second function above the ln. So second, e to the x, hit enter. We already have our y equals x. We can keep our window the same, and let's look at our graph. There's our log. It looks very similar to base 2. There is the exponential, very similar to 2 to the x, and there is our line. So again, if we sketch those points, it's going through the logarithmic function, goes through here. And our exponential function, which I will do in green, we know the exponential function always goes through the point 0, 1. They are reflections of each other across the line y equals x. So the purple is the logarithmic, the natural logarithmic, so the ln, and the green is the exponential with e as the base. So in example 5, it says using the logarithmic function f of x equals negative ln of x minus 2, find the domain of the function. Well, we know in this case that our domain of any logarithmic function is the same as the range of the exponential, and the range of the exponential is 0 to infinity. So I know that x minus 2 must be greater than 0. So if you add a 2 to both sides, x must be greater than 2. Then it says, without actually performing the transformations, describe what each change does to the parent function. So let's look at this. The parent function is f of x equals ln of x. So f of x equals ln of x would be the parent. So let's look at what has happened. There's a negative in the front of the entire thing, so that takes it across the x-axis because the y was made negative. Remember, the whole side is the y. Here, this is a horizontal shift, and it's going right to. That's the one that's counterintuitive. So it works the same with logs as it does with any transformation. Let's look at our second special case, which is the common logarithmic function, and that is when the base is 10. Y equals log of x if and only if x is equal to 10 to the y. So in your graphing calculator, we're going to do this one more time. We're going to graph, I'm right here, y equals log of x. So in other words, if you have y equals log of x and there's no base shown, it's implied that it is a 10 unless otherwise stated. And then graph y equals 10 to the x and y equals x. So let's get our graphing calculator here. Go into y equals. We will clear the first one. We'll clear the second one. We'll keep the third one. And so let's go back up and we're going to type in y equals log of x. Remember, I don't have to put in a base because if I don't, it assumes I mean 10, and I do. And then we're going to say y equals 10 raised to the x power. Let's change our window a little bit. Let's change our window to -4 and 4, 1, 2, 3, 4, 5, and scale of 1, and then -5 to 5. Let's look at our graph. There is the log, base 10. There's the exponential, and there's the line y equals x. It's basically the same thing again. The log goes through this point, 1, 0. Looks like that. The exponential goes through this point. It is its reflection of the purple one. And then the line y equals x goes right from quadrant 3 to quadrant 1 through the origin, and you can see that it is a reflection again. So the conclusions are, again, that the log is the inverse function of the exponential. All right, let's look at an application problem where we're actually going to be using logs. It says the blood alcohol concentration, which is called the BAC, is the amount of alcohol in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. Now, I know this sounds very complicated. It really isn't. I just want you to understand the meanings here, and then I'll show you how to do it. Is very simple. For example, if an individual with a BAC of 0.02% is 1.4 times as likely to have a car accident as an individual that has not been drinking, the relative risk of an accident with a BAC of 0.02% is 1.4. So those two numbers go together. Recent medical research suggests that the relative risk, which we're going to call capital R, of having an accident while driving a car can be modeled by this equation. R equals E to the kx, where k is a constant, just like when you were learning variation in intermediate algebra. R equals e to the kx, where x is the percent of concentration of alcohol in the bloodstream and k is a constant. So let's look at how we can work this problem. This is actually quite interesting. Medical research indicates that the relative risk of a person having an accident with a BAC of 0.02% is 1.4. Find the constant k in the equation. So our equation is R equals e to the kx. This is R, this is x, so let's figure this out. So we're going to replace R with 1.4 equals e to the k, and then our x is 0.02. Now, what's interesting here is that in order to solve for k, notice it is clear up in exponent land. So it's like, how do you get it on the ground? One of the things that you can do is you can take the ln of both sides. Just like you multiply both sides of an equation, you add the same thing to both sides, you can take the ln of both sides. So I'm going to say ln of 1.4 equals ln of e. And one thing you need to know, I'm going to write this at the top, is that ln of e equals 1. They almost cancel each other and equal just a 1. So now these make a 1, and it also causes, so let's write ln of 1.4, it causes this side to come down on the ground, so to speak, 0.02 k. And now to solve for k, obviously all I have to do is take ln of 1.4, and I'm going to divide both sides by 0.02. Do that in your calculator. Let's get out of our graph. Let's take the ln of 1.4, close the parentheses so it knows that you're through with that part. I like to hit enter here so as to make no mistakes. And now divide it by 0.02, and you will see that you have 16.82, etc. So k is equal to 16.82. That is our constant that we will use in parts B, C, and D. So in part B it says, using this value of k that we just found, what is the relative risk if the concentration is 0.17%? Starting with our equation, r equals e to the kx, we are going to fill in r equals e to that we just found k, 16.82, times x, which in this case is 0.17, or r equals e. Now, you can either multiply these first, or you can do this in your calculator. You're going to say e, which is right here on the ln key. That brings up the e. And what do I want to put up there? I want to put in the exponent land, let me move this over, 16.82 times 0.17. That's all up there in the exponent land. Hit enter, and you will see 17.45 or 17.5. So the relative risk, so this would be, I didn't finish this, but whatever that was multiplied, okay? R equals 17.5. That is your relative risk. Using this same value of k, what BAC corresponds to a relative risk of 100. So we start with A equals e to the kx. We know the k. We know the r this time. So 100 equals e to the 16.82x, filling in. And we learned up here that we can take the ln of both sides to bring this down on the ground. So ln of 100 equals 16.82x. Divide both sides by 16.82, and I get x equals, let's go into the calculator, I need ln of 100, and now divided by 16.82, and that gives us 0.27, etc., etc. So that means that x equals 0.27%. So if you had a blood alcohol content of 0.27%, your relative risk would be 100. All right, the last one says, if the law asserts that anyone with a relative risk of 5 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI? Okay, so this is the relative risk. So 5 equals e to the 16.82x. We're going to take the ln of both sides. So ln of 5 equals 16.82x. Divide by 16.82. And we get x equals, if you go into the calculator and you do that, ln of 5 divided by 16.82, you get approximately this. Now, what does that mean? This is important. It means that a driver with a BAC blood alcohol content of 0.096% should be arrested and charged with a DUI. So I'm going to put equals DUI. And I think you know that in Florida, it is not that high. If you'd like to see a summary of logs, look on page 448 of your textbook.